So friends, in my previous video about the same correction, I did that for physical chemistry. So guys, in this video I shall be doing that for inorganic chemistry as well as organic chemistry. So guys, please visit the video description, or better say go to the video comment section of this particular video on YouTube. Guys, you will see the link to watch all my full playlists about advanced level chemistry, and also the best hints that you can use to have A grade in the subject. Okay guys, without further ado, let's dive straight into the video. Okay, the question 3, which was inorganic chemistry section, reads that this question concerns elements across period 2 and 3, group 4 and of chemistry, and the elements sulfur and nitrogen. We should define electronegativity of an element. Let's start, guys. So for instance, electronegativity of an element is simply the ability for an atom to pull a pair of electrons in a covalent bond. Okay, it is the ability of an atom or element to pull a pair of electrons in any covalent bond. Wait, the Roman 2 is saying that we should state and explain the trend in electronegativity from left to right across the period 2 of the periodic table. Okay guys, let's start with the trend. What we are going to say, friends, is that the electronegativity, guys, simply increases from left to right. And friends, the reason for that is simply due to an increase in the effective or the nuclear charge, as well as a decrease in atomic radius. Keep in mind that atomic radius, friends, simply decreases from left to right as you move from one group to another of the periodic table. So that decrease, guys, accounts for the fact that electronegativity, guys, increases from left to right. Okay, the next part is saying that that's the B part, is saying that that for the period 2 and 3 oxide, we should give the formula of an amphoteric oxide in period 3, neutral oxide, and that. Okay, so guys, for an amphoteric oxide in period 3, guys, we simply have aluminium oxide. If they're asking for an amphoteric oxide in period 2, guys, therefore means beryllium oxide will be the best option. But since they're talking about period 3, aluminium oxide will serve the task. Then a neutral oxide in period 2, guys, the neutral oxide must be no other oxide apart from carbon monoxide. If you're talking about in period 3, therefore silicon monoxide has to be the best option. But in this case, since period 2 is involved, means carbon monoxide is the best. Then the Roman 3 is in that a period 2 oxide which causes acid rain. So guys, it should be no other guy apart from nitrogen dioxide. This is the best guy that we know about acid rain, right? Good. Okay, the C part is saying that we should define first ionization energy. So guys, it is simply defined as an enthalpy change when 1 mole of electron is removed from 1 mole of gaseous atom to form 1 mole of gaseous ion unipositively charged. So guys, the key things to take note: your definition must have moles written that's your definition must have moles written 3 times. Okay, it must have more, guys, written 3 times. And please remember to give this definition if the equation should come, which you should expect it. Okay, the Roman 2 is now should sketch a graph of first ionization energy of across period 2 and 3 of the periodic table from lithium to argon. But friends, I want to play that I will simply sketch that for period 2 only, namely from lithium to neon. Okay, then you will do the rest as an assignment. You are going to continue from sodium onto argon. Okay, great. Okay, let's have our axis displayed. This is going to be the first initial energy. This is going to be the elements. So we have the elements displayed, guys. We have lithium, beryllium, boron. Oh my god, guys, here has to be carbon. Okay, please remove the A. The A that this laser is directly on, please remove it. Okay, these other ones are good. So guys, we have that for lithium here, that for beryllium up there. We have boron, which is less than beryllium, guys. Let me know in the comment section down below why that for boron is less than beryllium. We have calcium's own is up there. Nitrogen, oxygen is also down compared to nitrogen. Let me know why it is so. Okay, let's connect them, guys. We connect like this, connect each of them so that the curve has this particular shape. Okay, that's it, guys. That's the graph. That's the required graph. So the next part simply wants us to state the general outer electric configuration of group 4 elements. So we have it as NS squared NP squared. Great, that's it. Then the other part, friends, is saying that we should give an example of a group 4 compound, that is A, strong reducing oxides. Then the other, we have covalent chloride, which does not hydrolyze in water. So guys, generally, friends, group 4 oxides are very difficult to undergo reducing properties. But however, guys, we have two of them. We have tin oxide and we have lead oxide. But in this case, guys, we go with tin oxide. Then the covalent chloride, which does not hydrolyze in water, guys, a best example in that case is methane. Okay, methane does not hydrolyze or even dissolve in water. It does not, guys. It's insoluble in water and does not even hydrolyze. Then the Roman 3 is saying I should write a chemical equation to show the amphoteric nature of lead oxide. Okay, guys. So what it simply does is that, okay, let's have lead oxide plus this alkali, guys, which plus the alkali, guys, plus water, which gives us PbO4 2 minus. Okay, that's it, guys. That's it. That's the required equation, guys. You can see that what has been formed in this case is simply uh, complex, right? A complex in this case, guys, has been formed whenever lead react with this alkali in the presence of moisture. That's water. Okay, so that is what has been formed. Great. Okay. Assignment, guys, I want you guys to write the other equation to show when, because in this case the lead in this case is acting like an acid in this case because it has neutralized a base, right? Good. In this case now, I want you guys now to show me the other reaction to show when for lead oxide act now as a base. In that case, it has to realize it has to neutralize an acid, right? And in that case, a salt has to be formed. So that's just a hint in which I'm giving you guys. Okay, so please write it in the comment section down below, or just simply tell me the compound that will be formed in the comment section down below, guys, so that if it is wrong, I'll give you what is correct. If it is correct, guys, I'm going to give you a big like or a big heart for that. Okay, let's go to the next question, guys. Let's go. The next question is that we should give two uses of nitric acid. The Roman 2 is that the Haber process is used to convert nitrogen to hydrogen to ammonia. We give the source of the raw materials. Okay. Okay, guys, let's start by naming the use of ammonia. So, guys, the first use is that ammonia is used in the manufacturing of fertilizer. We have typical fertilizers such as potassium nitrate. We have even the ones like ammonium sulfate. Okay, that's still a fertilizer from which it is manufactured from nitrogen. Okay, so let's give the others. Then that nitric acid is used in the manufacture of dyes. Okay, yes, it's used from that's the use of nitric acid. Okay, good. Okay, so the Roman 2 talks about, but let's just give number 3. Maybe this one might come in handy. We have nitric acid, friends, which is used as rocket fuels. Okay, so most of these people that launch rocket into deep space or just launching rockets which eventually propel themselves, guys, the component of their fuel, guys, has nitric acid in it. Okay, so we have nitric acid. Okay, now let's look at the next question. The next question simply talks about us to get the asking us where we can get the raw materials needed for the industrial operation of ammonia, of which they are nitrogen and hydrogen, but we have to tell them the source of those raw materials. Okay, so let's start with the first. Let's start with nitrogen. So for instance, nitrogen is simply obtained from the fractional distillation of liquid air, while hydrogen gas is obtained from natural gas. Okay, these are the sources. Okay, now the Roman 3 is saying that we should give a named compound of sulfur which has an oxidation state of positive 6. So guys, there are a lot of compounds out there. I think the best one for us to give, guys, is simply sulfur hexachloride. Okay, sulfur hexachloride, because we have SF6. It's very easy to detect this one, because if you calculate the oxidation state of this sulfur, you see it's going to be positive 6. There are so many others, guys. Please write some in the comment section down below, guys, for me. Okay, the Roman 4 is saying that we should write an equation to show how sulfur dioxide brings about acid rain. Very easy, guys. We have sulfur dioxide plus water, which gives us sulfurous acid, and this is the acid rain in question. Okay, all right, guys, that's it. The next part wants us to is saying that the elements, so lithium up to calcium, are called S block elements. Why are they called S block elements? So friends, they are called S block elements because their outer electrons are filled in the S suborbital, okay, or in the S orbital. That's the reason. If they are filled in the p orbital, they are p block elements. If they are filled in the d orbital, they are d block elements. Great. Okay. Next part is saying now she use equations only to show how sodium and beryllium react with water. So guys, sodium simply reacts with water to give us sodium hydroxide, and there's an evolution of hydrogen gas. That's it. This is the equation. Now guys, the next one obviously was a trap. So guys, in this case, does it mean that the beryllium also reacts with water to give us beryllium hydroxide plus hydrogen? No guys, no. This was obviously a trap, okay? So guys, beryllium, as you all know guys, does not dissolve in water, so no reaction occurs between beryllium and water. Note guys, beryllium does not react with water, okay? It does not. So this was just a trap in which they were setting. The next part wants us to state and explain the trend in solubility of the group 2 sulfate down the group. So friends, solubility simply decreases. The trend is that it simply, the solubility of sulfate guys simply decreases down the group, and the reason guys is due to an increase in lattice energy and a decrease in hydration energy. Great. So for instance, in terms of you comparing this comparing the solubility of ionic compound guys, you need to compare them only in terms of their hydration energy and lattice energies. Okay, only guys, these are the two parameters in which you compare them. If the substance is more soluble, means that what means that hydrogen energy is more than lattice energy. If the reverse happens guys, means lattice energy is above hydration energy. Great. So guys, that's it for this section. Let's go to the next, friends. Are you ready, friends? Let's go. Okay, the second but not the last is saying that this question concerns the group 7 elements or halogens. Here are their representations. Should give two reasons why fluorine exhibits only one oxidation state in all its compounds, whereas the other halogens show several oxidation state. Okay. So guys, how do we answer this question, guys? What do you think is the best way we can answer this question, guys? What do you think? Hey guys, what do you think? Hey guys, what do you think, guys? I'm waiting. What do you think? So friends, what do you think? Please write your answer in the comment section down below, guys. Let me know what you are thinking. But all right, maybe I should tell you guys. Maybe I should give you guys two reasons, right? Okay, the first reason is that what, guys, fluorine simply lacks available d orbitals, and secondly, guys, fluorine has a very high ionization energy. Great. So guys, these are the two important reasons that you should give. Okay. The next part wants us to write the balanced chemical equation to show the separation of hydrogen chloride from sodium chloride and hydrogen iodide from sodium iodide. Great. Okay. Let's start with from sodium chloride. We simply need to take any metal chloride such as what has been provided and react it, guys, with H2SO4, namely concentrated sulfuric acid. So doing that, we have sodium chloride plus sulfuric acid giving us sodium hydrogen sulfate plus HCl. That's what we have. So in this case, guys, our HCl has been produced, which can be collected as a gas. Okay. Then the next, guys, is sodium iodide. Sodium iodide. We have hydrogen iodide for sodium iodide. So in this case, guys, we cannot prepare it by this method. We cannot prepare it by this method, guys. There's going to be some problems that are going to arise because in this case, guys, the iodine, guys, can be easily oxidized. In this case, friends, if we use iodine, what we are going to get will not even be hydrogen iodide, but it's going to be iodine. It's going to be iodine itself. Okay, if we want to prepare sodium hydrogen iodide by this method, we're not going to get hydrogen iodide. We are going to have the same iodine itself. So it's going to work in a counter direction to what we actually expect. Okay. So to prepare hydrogen iodide, guys, what we are going to do in this case is that we are going to simply react this sodium iodide, guys, not with H2SO4, guys, but with phosphoric acid. When we do that, we are going to have sodium iodide plus phosphoric acid. It's going to give us sodium phosphate plus the hydrogen iodide, which is what we want. Okay, this is what we want. So we can simply collect this. Okay. The next part now is saying that we should explain why our equations in Roman 2 and Roman 1 are similar or different, which is why these two equations are similar or different. So guys, are they similar? No, guys, they are different. Why? Let's account why they are different. Okay. So guys, for us to say, we will simply say that this our sodium iodide, guys, cannot be prepared in the same manner as hydrogen iodide, because this guy is a very strong reducing agent and it is oxidized to iodine if you dare to prepare this guy by the method which we use to prepare hydrogen chloride. That's it, guys. That's it. The next part was us to account for the following. Hydrogen fluoride is much weaker acid than expected in aqueous solution. So guys, the reason for this is simply because hydrogen fluoride has weaker is weaker acid in aqueous solution because of the presence of it's simply because, friends, oops, guys, there was a part here that was talking about hydrogen bromide, while it is a much weaker acid compared to hydrogen bromide. Okay, so it is simply a weak acid compared to hydrogen bromide because the bond between this our hydrogen and fluorine, guys, it's very short and does not break easily, whereas that for bromine, guys, is lengthy, guys, and can break easily. So here was supposed to be HF, please, not HBr. Please do this correction, okay? Here has to be HF. Okay. So guys, as I was saying, please, hydrogen fluoride, guys, is the bond between these two guys is very short and does not break easily. Note that the strength of an acid depends on the ease through which the bond between hydrogen and that anionic part, guys, can simply get broken. Okay, because the more this acid can release H plus, the stronger it becomes. But you can also account, you can also say that that is intermolecular hydrogen bond present between hydrogen fluoride, so it is not difficult for the bond between both of them to break. Okay, that's it. Now the next part is saying that why hydroiodic acid is stronger than hydrochloric acid in aqueous solution. So the same thing goes, guys. We'll say that that's hydroiodic acid is a stronger acid than HCl because the bond between Hi is longer than that between HCl, and as such, guys, it breaks easily, which permits the release of H plus ions. Wait. The next one wants us to write balanced equations for the following reactions: iodine and hot concentrated potassium hydroxide. Okay, let's start. So in this case, guys, we are going to use just the ions, okay, just the ions that are actually reacting. And in this case, guys, it's a reversible reaction, okay? Please don't forget. And this reaction is a clear example of how do they call that reaction? Of disproportionation reaction, in which there are multiple oxidation states of the same compound that which gets oxidized and reduced at the same time. This is a disproportionation reaction. This is it. So with hot concentrated potassium hydroxide, guys, a halide and halide 5 ions get produced, and this is the halide 5 ion that has been produced because the oxidation state of iodine in this case, guys, is 5. Okay, it's 5, please. That's the oxidation state of iodine in this compound, 5. Okay. For chlorine, guys, with dilute potassium hydroxide, guys, we simply have the halide ion being produced and halide 1 ions. So in this case, we are going to have just our Cl2 plus potassium hydroxide, which gives us potassium chloride plus potassium chlorate plus water. Wait. So guys, these are the things that gets produced in the process, guys. Please balance the equation. The equation is not balanced, okay? Please try to balance their equation. Wait, try guys, try. That's it. So guys, that's it for the video. That's it for this particular session. Let's go to the next question, guys. Let's go. Now the last part is saying that transition metals are located between group 2 and group 3 elements of the periodic table. Why are zinc and scandium not considered as transition metals? Okay guys, let's go straight to the point. So the reason is that the stable ions of zinc, which is zinc 2 plus, guys, has a field d subshell y. Scandium 3 plus has an empty d subshell. Great. So in that case, guys, the two of them are d block elements, yes, but they are not transition elements. Great. This is the reason. Okay. The next part is saying that we should explain why it is easier to oxidize Fe2 plus ions into Fe3 plus ions, but not easy to oxidize the manganese 2 plus ions into Mn3 plus ions. So guys, the reason is simply that Fe2 plus ions are easily oxidized to that because our Fe2 plus ion, guys, contain a partially filled Z subshell which is unstable and can permit the removal of an electron to be stable. So guys, note that half-filled orbitals are more stable than partially filled orbitals. Great. So in this case, Fe2 plus ions have a partially filled orbital, and so it is unstable, and it reacts slightly to anything that makes it to attain Fe3 plus and becomes stable. Okay. But friends, whereas for manganese 2 plus ion, guys, manganese 2 plus ion, guys, has a half-filled d orbital which is more stable than the partially filled d orbital in Fe2 plus. So since manganese 2 plus ions already has a half-filled d orbital which is more stable, so it does not easily undergo further reactions to change its oxidation state because it is stable. Okay. The next part wants us to define what a ligand is. So guys, a ligand is simply an anion or a neutral molecule with at least one lone pair of electrons which is capable of being donated to a central metal ion to form a dative bond. Okay, that's a ligand. Then the next part is simply saying that what property enables some transition metals ions to be used as homogeneous catalysts in some reactions. Okay guys, the reason is because of the presence of incompletely filled d orbitals and the ability to vary their oxidation state. Great. So for instance, you notice that during chemical reactions, catalysts are being used, right? And the oxidation state in such a case, guys, gets varied. For instance, during the Haber process, you notice that vanadium pentoxide is being used, right? It undergoes so many different oxidation states, different variable oxidation states just before the reaction goes to completion. That's it, guys. That's it. So the next part is saying that cobalt forms complex compounds with the formula that what is the coordination number of cobalt in the complex. So guys, the coordination number of copper in this complex, guys, is simply 6. Don't get deceived by the chloride minus we have outside here. Okay, it does not affect any, it neither affects the name of this compound or its coordination number. It is simply there to balance the charges to ensure that this molecule is neutral. Okay, so in this case, to write the coordination number is 6. Now they are talking about the equation for the reaction between this complex ion and silver nitrate. So for this is simply a test to show that chloride ions are being present. So in this case, we have the complex with silver nitrate, which gives us this our Cl minus, guys, simply gets replaced by the nitrate ion, then silver, then takes chlorine. So this is what we have. Okay. They might ask us what we expect to observe. What we are going to see at the end, guys, is simply going to what a white precipitate of silver chloride which will be formed. Okay, a white precipitate. Okay. Now they're asking us, they're saying that we should write an equation to show the reaction. Okay, that's been written. They're asking us the type of isomerism that this guy could exhibit. So guys, since we already have our two chlorine atoms here, right? So we can displace them along the structure anyhow, which simply helps us to identify the isomerism being geometrical isomerism. Namely, it can undergo both the cis or trans. Okay. So guys, that's it for this video. That's it. Like I said, as soon as this video ends, you see that to watch organic chemistry and the rest. Guys, have a blessed time, guys, and good luck as you prepare for your examination. Humble Mark.